All right, welcome. So a couple of things I want to point out this week. So let me drag my screen across for week 13. So I did pull some grades across manually to about week 9 out of Cengage. I will probably pull all the way till week 12 this weekend. And it is kind of an interesting data processing process because it's not easy to do. Thank you, Cengage, for not deciding to work in this course. There are only 2 assignments and a quiz. I have pulled all the labs. Those live virtual labs are out, gone, done for now. The other thing that I did, if you look on the discussion boards, I didn't put a discussion board in for week 13. I moved it to week 14 and gave you a little bit of break. And so we'll have a discussion board next week, and then we have a final. We're almost done, almost out of here. The final will be available online for both on-campus and off-campus students. With our quarantines and viruses and everything else going around, I wasn't sure what was going to happen, so I've created a final that will work for all the students, and it'll pop open that week of Thanksgiving. So we'll talk about that more as we get to it. So this week we're going to talk about networks. What a surprise. We're going to focus on some performance issues. Somewhere I have a PowerPoint ready to go. So this week we're doing this idea of performance. How do I tune my network? How do I make it as effective and fast as possible? How do I recover from issues? And at some point, something is going to break. Guaranteed. The more pieces we put together, the more likely things are going to break because you have more items to break. So we're going to talk about some tools that you can use, how you can configure things, network availability, how we increase that. Because there's nothing worse than walking in and you're a business, you're trying to do some work, and all of a sudden the network's down or the internet's down. And so we're going to come up with some ideas and thoughts that will make this process a little better. So some of these seem common sense. So our goal, we want to increase efficiency, increase the ability to move data, increase the availability, in other words, less downtime. We know that downtime costs money because we have employees that aren't able to do their job. So downtime is expensive. Data loss is very expensive because then we have to recreate work. We want to figure out, can I predictively look at this network and see what might happen in the future? So I can make suggestions, improvements before we have issues. So network management is really that idea that we're monitoring, we're assessing, we're trying to manage in some way proactively our network. So we have some tools that we can use, and there's a lot of vendor-specific tools that we can buy. There's things like SolarWinds and some of these others that are prohibitively expensive. There's also some ones we've even experienced a little bit. So you guys have seen Spiceworks. Spiceworks doesn't do all kinds of network optimization, but it does do a few pieces of it. How much you invest on this network depends on the size of the company and the types of data availability you need. You know, if you're a couple of people in an office, it's certainly different than if you have 500 people all waiting on the network to do calls, inbound calls for Amazon, for example, or something like that. So network management. Well, it gives us that ability to control who has what access, what resources are available, what printers do I give people access to, what files, what storage, what scanner systems. Hopefully we can look for hardware faults, and we know at some point electronics will fail. And how do we predict that, and how do we monitor it to see when things fail to minimize our damage. We also are going to introduce a term called QoS, quality of service. So quality of service is that ability for us to prioritize traffic. We can prioritize it based on a lot of different characteristics, but primarily we think about audio as being the primary driver for QoS. So I need my audio packets, so whether it's phone or whether I'm doing some kind of conference calls, whatever it is, I need those to be optimized, and I need them to get there first. If your email takes a few extra seconds, nobody's going to care. If your funny cat meme takes a few extra seconds, nobody's going to care. We also go into this horrible thought of, how do I maintain records? What is on the network? What are things like passwords on all these systems? How are they configured? And if we don't have those records, trying to update or manage that network becomes nearly impossible. So you almost have to be a detective to go backwards to try to figure out what's going on. It's not uncommon for those records to not be available, especially if you have a network that is managed by a third-party company. You no longer use that company. Those records have been known to disappear, which makes life interesting for the next company that's coming in or your own internal IT staff. So part of that, when you set up a contract with a vendor to monitor and manage and maintain your network, make sure that you own those records, that you get copies of everything. That way, if they close, get fired, whatever happens, that you are able to get that data back. And then we know that we're going to have to do upgrades. We know we're going to have to do maintenance. We need to look at our environment and figure out what time works. So if I'm a 9 to 5 business, doing it at 1 o'clock in the afternoon, probably not a great time. So a lot of times we end up doing these things, and it's one of the downsides to being IT is sometimes you get stuck doing things after hours. Well, there are businesses that there are no after hours. And so you need to come up with a plan. How can they still function? So think about something like a hospital. A hospital has to keep running. It can't go, well, man, you guys are going to do an upgrade to the router. Well, we're just going to shut down and kick all the patients out. But there are times that are easier, and usually those are nighttime hours. But you need to come up with a plan with that staff that's going to be there so that when they know that the network's going to be down or your router's going to be down, do they have backup models in place? And you think, well, yeah, they need the internet to, maybe they need to send an email. Well, that's not a big deal. That can wait. But a lot of these systems are now remote. So things like CAT scans get sent off-site from most hospitals to a service. Well, if the internet's down because you've taken the router down and they have a crash victim, do you have a backup plan for getting that data to and from those people? So we need to think about that in terms of that availability. What can I do? If you've got to take the phone system down on a planned outage at a 911 call center, what do? So sometimes ahead of time, you can actually put in the newspaper, you can route it to a cell phone or something else, so you can come up with a preventive strategy to minimize issues. So what kind of tools do we have? So a network monitor sits on our network and it monitors traffic. So it's looking at quantity, it may be looking at types of traffic. So we can even do that with Wireshark. We could mirror off all of our traffic onto one PC using a switch, and we could monitor that traffic even with something like Wireshark. So typically, network monitor is one device, so one computer, even though we're mirroring multiple traffic in. We can also do protocol analyzers. So SolarWinds, for example, has the ability to monitor all of your traffic between a server, clients, between two computers, between two devices. So we can start to look and see what that traffic, what's going on our network. And a lot of times we find weird things. So we may find, for example, we have a network card in an old computer, and that network card is actually broken. It doesn't work right, and it's just sending a lot of traffic back and forth. You can find out a lot about what's going on that network. It's kind of like doing the EKG on a human. What all kinds of things are going on that network. And again, one of the biggest tools we use really is Wireshark. So, or something very similar. So, we can do wireless monitoring. What's going on our wireless network? What do we have going on there? So, this idea up here, notice they say something called a network tap. That's really that idea of we're mirroring out every piece of traffic that goes across there. So all the traffic between, in this case, a router and some kind of switch, we're pulling it out and we're monitoring every piece of it. So here we're showing it using port mirroring. Here they've put a network tap. In other words, it grabs the data and then sends it on. They both can do essentially the same thing. You're getting all of that traffic going across there. The one advantage to the network tap over the mirrored port switch is those switches pull off VLAN tags. So if I need to know what's going on in VLAN tags, a network tap, in other words, where I'm grabbing it directly, intercepting the entire data stream, has an advantage. And so that might be one case where it serves a little advantage. However, that network tap, the way they have it sitting in here, isn't going to grab all the traffic that's going across that switch between items. It's only going to catch traffic going inbound and outbound. So depending on your needs, that may be what you want. You want to monitor all the traffic going in and out of our network, and you want to see what's going on. So typically we monitor the wireless network, not the way they're showing here, but we would actually put a tap or mirror the traffic going to those access points. If we've actually encrypted it correctly, we shouldn't be able to intercept a whole lot of traffic just wirelessly. We'd get the traffic, we just wouldn't be able to decode it. Now, there are times we'll take a laptop or a special device and actually go out on the network, on the wireless network, to see what performance issues we're having, to fine-tune that wireless network. So we certainly will do that also. So you've seen that term port mirroring. We can set it up on almost any of the managed switches. So 48 port managed switch, anything above probably $800 or so in terms of cost. If it's a layer 3 managed switch or even a layer 2 managed switch. Managed means we can get into it and we can make changes to it. An unmanaged switch means it doesn't get an IP address on our network. It doesn't do anything except send traffic. We have no control over it. And so in this case, for port mirroring, that doesn't help us. And it doesn't let us do a lot of other things. Most of them won't pass things like VLAN tags correctly. So port mirroring is an important tool we use. It's also one of the best cyber tools we can get a hold of. If I can get into your network and I can get a hold of your switch and you don't have anything but default ports set up, or your administrative login, if you're just using default, which is all too common, unfortunately, and I can mirror all that traffic to a specific port, I get everything on your network for the most part. Yikes. Yikes. So a tap, same way, I could, if I have physical access, I could certainly install that. So one of the funny words or funny things we have to talk about in here is your network interface card. And not all network interface cards will do this. So if I'm going to set up something like a network tap, or I'm setting up Wireshark on a computer, I really have to make sure that the network card will run in what's called promiscuous mode. Typically they're set up so if that addressed information isn't addressed specifically to them, they discard it. In promiscuous mode, they'll grab all of it and you'll be able to see it in that software. So when we installed Wireshark, there was a piece that was called WinPCAP. That's the piece that actually grabs all that traffic. And I had a few people that had some issues getting Wireshark to run correctly. And I think that may have been one of the issues, is they had a home computer with just an onboard NIC, and it wasn't able to switch to that promiscuous mode. It wasn't able to grab all that traffic. It would only grab the stuff addressed specifically to that machine. So that entire segment or broadcast domain, if we can use port mirroring, we can grab everything in there. So we can also grab just a ton of data just in here, because you get to see all those packets going back and forth. They're not all addressed to your machine, but they're out there on that network. And so you get to see a lot of that traffic that's out there. Well, that allows us to monitor that network, see what kind of traffic we have, what kind of speed they're transmitting, what kinds and types of packets. So do we have an ARP broadcast storm because devices aren't responding correctly? So it's not a bad idea to have in there. We can start to see what happens on our network during different times of the day. And you may see that your traffic peaks. You may have not enough bandwidth to support everybody. You may have users complaining, man, I couldn't get onto their shared drives. And so we can come up with some methods to allocate those a little differently. So what you're really trying to do is create kind of a baseline for my network. That's the first start, is what does it look like now? What does it still look like now? We can also set up alarms and other things to tell us what's going on. So if something triggers, we can send it to our phone or whatever else. So the other piece we can look at is we can see, man, maybe there's a couple computers in there that are taking up all of the bandwidth. So here on our campus, we have the dorm rooms, and we know everybody's going to go in there in the evening, and they're watching Netflix or Amazon Prime or Disney Plus or whatever it is they're looking at. We know that some of those services take a lot more bandwidth than others, and we can identify who has them, is using all that bandwidth. Maybe you have somebody in the dorms, and what they like to do is download BitTorrent files, and they're taking up huge amounts of data, and we could identify where those are coming from. And at business, sometimes you have those. Some individuals are trying to do things at the business they probably shouldn't be, or they're downloading a lot of data. Maybe there's a reason we need to look at them. So the other thing we can do is we can find out when there's errors inside of there. So we're looking at all that traffic. So we could have all different kinds of things. So are we losing packets somewhere? Discarded packets. In other words, somebody didn't accept them, so they die. So we know that those are out there. If we have a computer that continually is doing DHCP requests every 10 minutes, what's going on with that? Why is it losing its IP address? Is that computer restarting, resetting? So do we have runts? In other words, not fully formed packets. Do we have giants? So giant packets are bigger than our typical MTUs. Does it get passed correctly? Are we trying to pass them outside of our network? Is there an issue? Do we have ghost packets? Packets we don't even know where they're coming from, that we need to identify what that traffic is. And so depending on that tool, one of the most common things they do is actually send you a text. So SMS, short message service, that great thing we have on all of our phones that can send us a text and is a byproduct of the pathways on the cell phone signal, we can actually interface those in a lot of cases. So what it will generate then is some kind of a log. Now, our computer itself already creates a ton of logs, and we're gonna look at Event Viewer here in just a second. But those network tools also generate a log. And so we can look at all those. Everything you do on that computer creates a log entry, and we can see what's going on inside of that machine. The problem is we typically don't see these until it's far too late. So until something actually breaks, we don't typically look at those log functions. So Windows has Event Viewer. If you're in a Linux or Unix style environment, there's also logs. In fact, probably a little better logging functions in a lot of cases. So they use a function called syslog. It's probably, again, it's a little more robust in some weird ways. Which version you're using, they've moved around the location quite a bit. Usually they're in the var folder. Depending on the version, you may need to go look and double check. If you're using Solaris, obviously it's got it in a little weirder spot. But that documentation's out there. If I'm running Ubuntu, I can do Google search Ubuntu, where are my logs? Everything that happens on that computer then gets copied over here. So there typically is a GUI, and I'm going to show you what the event viewer, and you're welcome to try this along with me. And so that is just event. If I type in event at the Windows key, I get, it's actually in the right window. So this is my event viewer. This is for this local machine. And so this very first overview here, as it's still processing a little bit, gives me an overview. So in the last hour, I've had one error, one warning, 39 informational pieces, audits, and an audit failure of 4 items. And if I look over the last 7 days, holy cow, there's a lot of records that are being stored on this machine. So I can use this kind of as a drill down. So in this case, the error is our always handy Office 2016 licensing issue that I run into. So we have an odd pathway to the licensing server on our campus, what's called a KMS server, and occasionally it hiccups, like every day. So you'll see what some of those are, and you can actually log into each one of those and see what it actually does. So here we've got a distributed comm system error. And if I double click on it, then I get the list of errors and I can see what they are. The server Microsoft.Skype app did not register something. So you can see that there's a ton of those errors. We can look at them over here by administrative views. So here's an error that we could look at. Oh, popped up in the wrong window. Drag it over. So while we were trying to open a log file, we had an issue. It's not uncommon to have a ton of errors. Windows makes those errors, and the longer that computer's running, the more you're going to start to see as programs get installed, uninstalled. So there's application logs. So here we have our error, and so every time it logs an event. So already today, it's logged a whole ton of events just for today. So I can rearrange those by severity. I can rearrange them by ID. There's security logs. So here, the event occurs when a user performs a read operation on stored credentials. So in other words, I was able to log into this computer, and it tells me when that happened at 12:57 that was used. So you can see that we store thousands of things on your computer. So the system here, you can see what's going on. So it's also useful. These are useful in a lot of different applications. So I have an error, I have an issue. I can start scrolling through and I can figure out, drill down on these, and I can figure out what's going on with this particular computer. If it's on a server, I can identify issues because the server contains a very similar event viewer in Windows Server. So this is just a really handy tool. The other thing you can do, find out what software is installed, find out when people did something. So these are also a forensics tool that you can pull off of here if you need to. And hopefully that's not something that you get stuck doing. But you can actually customize these and get them to send all kinds of things. So that is Windows Event Viewer in the 30-second view of it. So it stores a lot of history, but unless unless we go in and we look at something, most of the time you're not going to get any error messages about that. So that's one of the downside is it stores all this information. If I don't go in and look at it, it doesn't really tell me anything. So unless something's going wrong, and then I go, well, let me look at your event viewer and see if there's a program that's crashing repeatedly. So one of the things that's happened is there actually are some third-party applications that can access those log files and probably do a little better than the built-in editor to take a look at them. So, a great resource on a computer. You can see what everybody's done on that machine for quite a while. So we can look at things locally. We can also look at it on an enterprise-wide basis. So an enterprise-wide means that we have something that's communicating with that network management and with every device on there. So routers, phones, switches, thermostats, whatever devices on our network, they're also sending back messages. So we use this SNMP, Simple Network Management Protocol, and it sends out a request and says, hey, I need some information about you. So you can ask questions. So it's collecting data from all of those managed devices. Usually they do it in what they call a polling, so every hour or every 12 hours or every day gets information. So we can even do things like your network managed system can tell you, hey, Brenda's computer down there, her hard drive's about full. Or Brenda needs toner in the copier. Those kinds of things can all be sent back. So it's all stored in a database, depending on which software you're using. So there typically is an agent that is installed. And so when you installed Spiceworks, for example, you can choose to install an agent on each one of those computers. That very tiny agent is what responds back and says, oh yeah, you're about out of printer ink. Or, hey, I just installed some software for you. So those kinds of things are all stored in that agent, and it communicates back. So this is what it kind of looks like. That agent sits there on that computer. The server says, hey, I want some information about you, and then it sends it back. The weird term is this idea of something called a trap. And I don't know where that originally came from, but what it really does is it means to me it's a push from that managed device back without being questioned. So if I set up parameters for things like overheating, hard drive full, whatever conditions I have that trigger it, then it sends a message back to my network management server. So a trap is really nothing but a pushed message that comes back. So different layers. So SNMP has different versions. What a surprise there. So it is in that TCP suite of software protocols. The version 3 is the latest. Version 1 out. Version 2 still very popular with a lot of equipment and devices. Version 3 does some encryption and is a little more secure. Because one of the other issues with this is if I'm on your network and I know about what your network is comprised of, can I do some bad things by using SNMP? And the answer is yes. So why do we use it? This sounds like, man, we're going to add more overhead. We're going to make somebody do something. And it's that ability to tune our network. Get our network as fast and as flexible as possible, minimizing our costs, maximizing our efficiency, maximizing our availability. But some of that we have to decide. What information do we need to collect? What do we not care about? And so that depends on that particular network. Maybe I don't care. They can take care of their own printer ink, so we don't care about that reporting. But I do care about hard drive space because everybody wants to store too much stuff. So I have agents that report back on that or send a trap when somebody fills up their hard drive. Well, before we know what we can do, we have to do a baseline. So that is that idea of what's going on in our network right now. It's the same kind of an idea. If you're going to the gym, you got to do a baseline so you know what you're capable of, and gives you an idea, how can I improve, how can I not improve. So some of the things you might see on there. How much traffic are we sending out on our backbone links? How much data are we sending outside of our network? How much data is coming in? What kind of protocols, what kind of traffic is going between different nodes or points on our network? What about errors? What are our error statistics? What kind of applications get used most frequently on our network? Maybe we find out, so we start monitoring our network, and we've bought everybody Microsoft Office, and we find out that nobody uses it. They're all going to G-Docs or Google Docs and using that. So it gives us that idea. What does our network look like? And so we'll get a lot of information, and you want to do it over more than just a single day. So a couple of weeks typically is what we look at. So we get data. So this is just daily network traffic in here. So one small piece of it, and we don't even really know, is this traffic leaving our network? Is this traffic going into our network? Well, in this case, I don't have any idea. It says, here's my baseline. So I'm going to interpret this as this is traffic that is coming into our network. That seems to make some sense. And again, we would look at inbound, outbound. But one of the things we notice on there pretty quickly is, can we tell when this business is shut down? And it's not shut down on a Saturday, Sunday. What days do they shut down? Sunday, Monday. And you can tell that from that traffic. So maybe we know that in this particular case, the way we buy traffic, if we hit more than 50 gigabytes, that we go over a price cap. Should we be worried about what's going to happen in the near future? Yeah. So it might be we need to increase our bandwidth in, if that's what this chart is showing us. We might also want to look at some of this data. Even during the work week, why are some days so much higher than others? What's going on our network? Because some of those days we were supposed to be off, so that Sunday there's a lot of traffic. Somebody hanging out in the office and doing something they shouldn't be doing maybe? Or are they going to work and showing up? Who knows? We need to probably figure that out, drill down, and try to figure out a little better about what we're looking at. So if I have these baselines, I can start to see what kind of data is being used. What kind of data are we using? We can compare it to past. So if we did a baseline a year ago, what's changed? Is it increased, decreased? Some companies actually have hired more employees in this COVID-19. Some have lowered the number of employees. So there is a lot of data out there. Which software we use. There's freeware, there's paidware. There's all different kinds of software we can get that we can manipulate and monitor. We can pull our router logs even and look. So on this particular system we're on here, if I go into our router, I can actually pull some data out of this. This router actually has some traffic analysis. And I can look at, in this case, it's showing me which items, if I look at receive, which computers in here receive the most data from this router as it's passing through here. And so I can see that 180.145, this one's got a lot of data coming in from some place called CloudFront and Amazon. So that is 184. So we could actually identify which one are our heaviest users. So this is historical data for a while. I can look at who transmits the most data. And notice in this case, I know that 103 is this station up here. I push out YouTube videos, but yet there's a couple that are nearly as much data. I can actually look at it over here, and I can look what's going on currently. So right now, because I'm uploading some data as we speak, I'm pushing out some, but I'm also seeing a number there. Somebody is receiving a ton of data on these right there, on these computers there. So I could look and I could see who's receiving the most data. Where is it going? Here's my current transmit rate and receive rate. So it gives me a little bit of data, and I can customize this, and I can then save it actually in the logs. So there's a lot of different pieces we can do, even on your router. Because I'll sometimes go to a router really quickly, because one of the problems we have is you'll have one or two users consuming all of the bandwidth, especially when you're in a smaller town, you don't have a large pipeline. It's pretty easy to saturate a 10 or 20 megabit per second line because somebody out there is downloading all these videos and fun things out there. So I can look and go, wow, why is there all this traffic for Netflix? Why do I have gigabytes and gigabytes of traffic for Netflix when we're at a business? Why are they watching movies while they're supposed to be working? So we have a whole lot of other software that will do far more advanced items, but that's just an example of where we can start at. So we set up that baseline. We've got ideas about how we're communicating, what we're doing. We're monitoring this traffic. Well, we're doing that for a couple of reasons. One, we know we need to keep up with whatever demand users have in that business unless we curtail them a little bit. Is it growing? Is it going down? Typically, we don't go down in data, unfortunately. We're always going to go up. Do we have enough bandwidth going in and out? And we can also then look at what kind of faults, what kind of things are going wrong on our network, and how do we start to correct those? And so that's kind of that idea, that baseline. It gives us where we're at, and it gives us a path forward, then how we can start to manipulate that data. So the most common way we start is with this idea of something called packet shaping. So packet shaping says, I'm able to see that data, I'm able to open up that packet, I examine it, and I see what kind of actual data it is. So I can hide data. I can try to say it's port 80 traffic, and maybe it's really Emule torrent clients or something else. What I can do then with it is when I can actually open it up, that packet, it lets me see what it is, and I can prioritize that traffic then. So I know that VoIP traffic, Voice over Internet Protocol, maybe gets the first, and Netflix gets the lowest priority for us. So we increase priority of the most important network traffic. We limit traffic for different time periods. We know that maybe 5 o'clock on a Fridays is very busy. Everybody wants to get online on Netflix, and so we limit some of that traffic. Maybe we see one traffic interface, and we need to monitor just it, and we need to pull it down. Because somebody over there in Morgan is downloading images of Ubuntu and other software distributions that are gigabits in size. We can limit that. So limit how much throughput they have. So we really kind of like thinking about this as kind of like the traffic cops. They're seeing the traffic, they're routing it correctly, and they're limiting you in your speed in some cases. It would be great if we all had unlimited bandwidth, but we don't. We don't. So here at the college, they have a couple hundred megabits per second, which sounds like a lot until you start looking at the bandwidth needs. So if I'm downloading high-def videos and I'm streaming them, that can be 25 megabits per second or more for each stream. Well, that means the entire campus, there could be 8 people watching a high-def movie, if that were the case. So we have to have some way to share those resources. So this is that kind of idea. So the other issue and why this becomes really important is at your house, you pay for your internet and it says, hey, you have up to 100 megabits per second. On a commercial side, you typically pay for a speed, and you can also pay to have that speed as a burst. So if I'm looking at this chart on the left, what I might be paying for is a 40 meg per second service, but I have burst capability to 50 or 60. But for all the time that I exceed that, I get charged a surcharge. And so traffic can get very expensive. So using things like those packet shapers is a way that we can maximize our data resources. We still get the same amount of traffic in. We've just kind of normalized it a little bit. And we've also routed traffic that we don't want, for example, on our network. We don't probably want things like BitTorrent clients on most typical networks. We want to eliminate them and make them go away. We talked a lot about this idea of traffic prioritization. In other words, how do I treat different traffic differently? So we can base it on a lot of things. Where it's coming from. So it's IP address coming in or out. So maybe I give the CEO prioritization on all his traffic just because we don't want him cranky. I could base that on his IP address. I could base it on the IP address of the destination or where it's coming from. I could use protocols. So some traffic gets priority, some doesn't. So maybe port 80 traffic gets priority, maybe VoIP traffic gets priority. I could use groups in like Active Directory to prioritize traffic. So students get one level of priority, faculty get another, and administrations get a level above that. That happens quite a bit. There are some flags in the IP packet we can use, the diff serve. And so we put a tag or a flag right in that IP packet. We use those VLANs that we've talked about. So most places, this is almost the most common way we prioritize traffic because we'll create different VLANs for different types of traffic. So your phone switch is on VLAN 100. Whereas data traffic's on VLAN 107 or something. And our guest wireless is way over there on 109, and we give it the lowest priority and the least amount of privileges. So we can also, if we're traffic shaping, we can do it by application. So we know that some applications time out really quickly. So how do we avoid those? So video, we know, time sensitive. We don't want video and audio. And actually, the weird thing is the audio part is the part that we notice the most. If we notice a few flickers in the screen, we don't really notice that much. So we may need more bandwidth, but sometimes we can cure it with service prioritization. So we want to give quality of service, QoS, to those services that we need. So they will get accurate data, they will get fast data, and the more we can keep the packets without having to be shuffled in order, it really is a benefit for that type of traffic. So if I have a layer 3 network, so my routers, my smart switches, I can use that diff serve to prioritize traffic. So IPv4 has the diff serve. There's actually a slightly different one in IPv6. Does the same thing. It allows me to prioritize traffic. So I put it right in the packet. Even if I strip off the VLAN tags, it's still in there. And so I can assign priorities in that routing services that is in layer 3. So there's even different layers of quality of service. So expedited forwarding is kind of the top dog. So minimum departure rates, in other words, I am sending it as quick as it is. I don't delay. Sometimes I don't examine the entire packet, so it gets pushed through. Assured forwarding, though, next layer down, but we're still looking at that idea of packets arrive where we try to get them to arrive in sequence. So that's less manipulation on the other end, but it's another layer down in our priority list. So in VLANs, if we're using VLANs, we can also assign a quality of service or class of service based on the VLAN. And so there's 8 different levels in the VLAN service, or in other words, 1 byte. And so there's a flag that gets set in that VLAN. So layer 2 techniques, so in other words, they're not between different points. They don't have to pass through a router, but they may pass through VLAN routing. So there is a flag that we can use for that. And the question always is, can we use multiple techniques? Yes. Yeah. Sometimes we even use things like our subnetting techniques, so we break apart those devices with different subnets. We break them apart with VLANs. We minimize the size of those collision domains, so we minimize the amount of traffic in there other than just our traffic of the class being sent. So the other piece that's kind of handy is not only do we want to prioritize that traffic, and we want to figure out how we need to route traffic, and we make sure we have enough bandwidth, we need that availability. It's got to be available. And if I buy a switch that fails, or I buy a router that fails, that doesn't mean that network is available. So typically, we talk about availability in nines as a percentage. So 5 nines would be 99.999% available. And so if I buy a service like Google Mail and I'm paying for it, or something like that, or an online service, they will tell me I have 5 nines of service. And that tells me 99.999% of the time that network's up, tells me how many minutes I can expect of downtime. Well, we have something very similar here. And so even on our own computer, you can actually see how long something's been running. If I go back to my router, you can actually see very clearly how long it's been since it's reset. See if I can find it real quick. So, must have hit a button there. So in this case, this router has actually been running for 9 months, 3 weeks, and 5 days. If I looked on here and I saw that was a Windows server with that much uptime, I would probably panic, because that means it hasn't applied any updates. Linux, which is what most of our routers like this are based on, that's not uncommon for it to be up at that length of time. But I can do the same thing on my computer. So if I have a Windows machine, and I look at the Performance tab, I can get the same information on a Windows machine. A Linux machine you can actually use, there's a command called uptime. You can also run at the command line. So in this case, this computer has been up for 5 days, 6 hours, and 11 minutes since it's been restarted. That can also tell me that availability. If I look at that and that computer's been restarting over and over and over again, that can tell me that there might be some kind of an issue with that machine. Maybe it's time to update, look at it, do some software updates. So typically on a Windows server, I'm used to having uptimes of a couple of months before we run into some kind of software update that has to restart. So Linux, there are updates that force you to restart also, but it's typically a little less. And so in the case of this guy, that's not uncommon. There are routers and things that are out there that are running for years without being without being restarted. So we can actually see that. Chunk, come back. So if I were in Linux, again, I can look and see how long it's been running. And if I didn't manually turn it off and on, why has it only been up for a day? Or why has it only been up for a short amount of time? And so it's, again, another way that we can do that. So high availability means that we expect that system to be available nearly all the time, or all of the time. So we want to build our network with some of these ideas in mind. The problem is making our network more available costs more money. And we all know everybody wants to save money. So it's a balancing act. Yes, there are routers that you could have up for years on end. Is it going to do what we want it to do? Hopefully. Is it going to cost more money to have some redundant capabilities? And so we'll talk about what some of those are. So a failure means that there's some kind of deviation. It changes from what we expect. So performance level turns off and on, doesn't start, whatever that failure is, it's some kind of failure. So fault is very similar. So a fault means something has malfunctioned. So we want to create fault-tolerant systems. In other words, we want it to go from, hey, there's a little glitch, to not completely failing. And so how do we do that? And the biggest way we do that is with something called redundancy. So depending on your level of spending, you can create a system that is very redundant. So some things are pretty common. Most high-end switches, most servers have at least 2 power supplies. One of the most common parts to fail. So power supply dies, they have a redundant power supply, it switches over to the second power supply, lights up on the screen, or there's an alert of some sort, and says, hey, your first power supply died. You don't even notice that anything has happened in that case. So yes, we had a piece fail, but the entire system did not fail. So that's what we're looking at here, is this idea of how long between failures, mean time between failures, and then here we have mean time to repair. So if it automatically switches over, we never have any data loss, we never have any issues, except at some point we need to replace that. And if we don't notice it, the next power supply fails, guess what? Then the entire system goes down. Well, what's interesting on these mean time to failures, on electronic components, they actually do something called a bathtub curve. So electronic components either fail typically initially within a very short period of time. So like the edge of a bathtub, they drop down, and then they don't fail for a long time, and then all of a sudden they start failing at some point in the future. And so typically if you buy something like a hard drive, it's got a mean time between failure. Hard drives may have a 300,000 hours between failure. That mean time between failure. Does that mean that every hard drive you buy is going to die at exactly 300,000 hours? No, it's a statistical number that says if I have a whole number of them, the mean of that is going to be around 300,000 hours. With that said, the more devices we have, that actually shortens that interval. And I know that seems strange, but if you think about it, if I have one car, the chance of it breaking, it's probably going to start in the winter, right? But if I had 1,000 cars out there and I went to go start every one of them in the winter, I'm going to have more cars that aren't going to start. The more parts we have, the more complex a system we have, the more chance for some part of that to fail. And the same way in our network, the more switches we have, the more servers we have, the more hard drives we have, the more chance we have of a single part to fail just because of that bulk item. So if we think about a good example of that, the space shuttle comes to mind. Everybody remember the space shuttles? It was probably the most complex project that NASA has ever undergone. There's over 1 million parts in the space shuttle. And when they actually started doing the failure analysis and trying to figure out what the odds are that some part would fail, leading to a major destruction or failure, they actually came up with that many parts and the statistical modeling, that about 1 in every 25 launches would have a catastrophic failure. And when you look at the number of launches and the failures they had, their math was right on. So if I had 1,000 hard drives, I would actually expect a failure a lot more often than every 300,000 hours. And if you look at companies like Backblaze or somebody that stores a lot of data and will tell you about their data, that's what you see. They'll replace several hard drives a week, and you can actually get a better idea on failure predictions. But these two numbers are kind of important, that mean time between failure and then how long it's going to take to repair. So some things, if I know I need to be high available, maybe I have a spare power supply for my switch, so I have one on stock. Maybe I have extra hard drives. Maybe I even have an extra switch, so I can minimize that disruption time. But it's all based on your individual company. If your company can survive being down a week while you're sending off something to get repaired, you're probably a lucky company. But if you're Amazon, 5 minutes could cost you $1 million in sales around Christmas, right? So I have to base what I purchase on that idea of what fits my particular company. So it really is that idea of redundancy. Critical components need multiple versions. It makes sense. If we can have them where they switch from one device to another automatically, even better. So power supplies are that common example of, hey, one dies, it switches to the other power supply. But it's costly. It really is costly. So that's one of the reasons if you go try to price a server, it's a lot more than an average home computer because there's redundancy pieces built in. It's designed to run 24 hours a day, 7 days a week, 365 days a year. Whereas your home computer, quite frankly, isn't designed that way. It doesn't have multiple fans that you can switch out while it's running. Some servers even have redundant memory, so if a memory chip dies, it just bypasses it and switches to a new memory chip that's stored in there. There's multiple hard drives, so if one dies, one will be pulled online and resurrected pretty quickly. So it's why we cost more money, but it costs more. And so there are a few anomalies in there. And one of the weird ones, I think, is Google. It's an interesting study. So a Google data center, they're not going to tell you, but the best guess is somewhere like Council Bluffs, one of their data centers, there's actually 2 in there, has somewhere around 400,000 servers. But Google does something a little different. So instead of making each device or each server high availability and redundant, they make the entire server redundant. So they will just power off an entire server, and then they go around on maintenance cycles and replace components then. So they just power it off. And so a lot of their stuff isn't redundant in the sense of each individual server, but most companies can't afford to have 400,000 servers. They have 1 or 2, and so they need that idea of redundancy. So it's an interesting model. So this is that idea of fault tolerance here. So a single connection to the internet. In this case, they're talking about a T1 line, which really nobody uses much anymore. But that connection has no redundancy. The next diagram down, actually we have redundant both firewalls, we have redundant routers, we have redundant switches, and 2 internet connections. different vendors providing us internet connections. If we're getting both internet connections, both from Windstream, it probably doesn't help us any. But maybe you have one from Windstream and one from Comcast or whatever other service you have. So you have the ability to stay up and running much longer. So one internet service. And so what you're trying to eliminate are what we call single points of failure. That idea that one thing can take down your entire network. All right, I think I will stop here for today. So take a look at, get back out of here, this week's assignment. If I get the right tab open. So you have these two lab simulations. One of them is working with Event Viewer, and the other one is actually looking at SNMP, Simple Network Management Protocol. So if I remember correctly, these are not the longest assignments we have had by any means. There is a quiz, and again, these items are just for your own. The review, the practice, and the reinforce are just for you to use. There is a final, and so next week we'll talk a lot more about the final and how it's going to work. But it is set up and it will be all online. So if you're on campus, you'll be able to take that final remotely. But it is due, I think I actually have the due date in there. If I remember correctly. So November 25th, 10 p.m. Central Standard Time, that final has to be completed by. So it will open up for about, I think I have it set up for probably 5 days to be open. So there'll be plenty of time. I'll send out plenty of reminders for that. All right. And then we'll figure out our schedule when I'll run the final sweep. That'll probably be the last. I will pull out Cengage and move all that over at the same time also. All right. Any questions? I would have to run I think the discussion board's like 20%, something like that. I don't know right off the top of my head. It's in the syllabus there, and you can see the points on the syllabus there. If I remember right, it's about 20%. The lab connections, the Cengage stuff, is about 30%, if I remember correctly. Altogether, there's almost 6,000 points in this class just because we use Cengage's point values to move them over. Supposedly, it was going to integrate, and then it's exploded, so that's always fun. All right, any other questions? Going once?